Good day, everyone. This is a recording of the panel data regression analysis. We're going to use the same file that we used before, and we're going to use the same data, which I shared with you, the JTrain data, the job training data. So the packages that we need are Tidyverse, Stargazer, Magritte-R, Haven, PLM, LMTest, T-Series. So this is a way to install packages. It tells us that for all of the for each of the packages listed here, okay, if it's available, okay, if it's not available, do not require yet, but install the package. Okay, otherwise, require it first, and then require it or load it. Okay, so after installing the package, you load it. So let's run this. Okay, so we're going to make use of the JTrain data, which I shared with you. So this is a CSV file, and let's load it to R and view it. And we have seen that it consists of several variables. Okay, there are all in all 23 variables. So this is a variable that records the scrap or the wastage of the company from years 1987, 88, 89. So that's the year here, and that's the company name. Our company code is F code 323232 here, and then etc. So you have here some data like employees, sales, average salary, and the one that we're going to use is log scrap. Okay, and then you have D89 and D88 total hours of training. Then we have grant and grant one. Okay, so two grants. Okay, so that's our data. And you notice that L scrap has NAs, log of the scrap. So we're going to remove those that are NAs. Okay, so JTrain, this is your compound assignment operator. And we're going to use the filter function from dplyr. So all the NAs will be filtered. When you filter, you remove rows. So JTrain currently has 471 observations. So if we filter those NAs, let's run this. And then let's load back JTrain. You can now see that JTrain has only 162 observations. Those that with NAs were filtered. So we can see here the log scrap here. So there are no more NAs or missing values under log scrap. Okay. All right, then let's go back to our codes. After we have filtered the missing values from L scrap, we now have a clean data. Okay, so there are only 162 entries, observations. So let's first describe and summarize our data. This is your pipe operator, Control Shift M. This means that JTrain and then get the structure. JTrain get the first 9 observations. And let's create a table Stargazer out of this. All right, so let's run this. So you can see here the structure of our data. Let me read it from this side. So this is a uh, special table. Okay, it's a data frame. And you can find here also some details about uh, the employees, sales, etc. Okay. Now what we're going to do is we're going to select function from dplyr selects the columns. So we're just going to use the lscrap total R's D88, D89. D88 is a binary variable which indicates if uh, uh, um, if there was intervention perhaps in 88 and 89. Okay, and then grant. So these variables are going to be used in order to uh, describe our L scrap, the log of scrap rate. This is the scrap rate. And then we're going to get the variation, which is the variable minus the mean, its mean, okay, and remove the missing values, okay, and then create a data frame out of it, and then create a table out of it. So let's see what this does. So gives us a summary of the L scrap 162. Total R's is 146, which means that there are some missing values here. Okay, and it measures the standard deviation, the minimum, and the maximum. Okay. All right. So the next code chunk measures or groups the data by term. So we start with JTrain data, which is, as we mentioned a while ago, this one. Okay, and then we group the firm, and then once again we select only these variables, and then we summarize. We summarize all to get the mean, and then create a data frame out of it, and then select by removing F code, and then creating a table out of it. So let's run this. Okay, so you have here the number of L scrap, and then the average. This is the average of the L scrap on a firm basis. Okay, this is the average total R's. This is the average D88. Okay, and then so that's overall variations. We can also get between variations. So this is for the overall. We can also get the between this one. So we group again by firm, and then select again those variables, and then summarize all the mean. Okay. I'm sorry, this is what we did a while ago. Yeah, then within variations, we group by. Okay, we group by, once again, we group by Okay. For the overall, we did not group by. Okay, so for the between variations, we're grouping by the firm. Okay, and then within variations, we group by firm, and then we select again these variables here, and then mutate all, okay, which means we're going to compute once again x minus the mean of x, okay, which is demeaning it. We're removing the mean, and then once again, we create a table out of it, and then we don't include the mean. Okay, so this is what we get. This is for all the observations. Okay, so in order to create a panel linear model, okay, there are three methods which we have discussed before. We have the pooled, we have the fixed effects, and we have the random effects. This video is more about the process of doing the regression and not the differences between those methods. It was discussed in a previous video. So let's first start with the pooled OLS, and we use the panel PLM function from the PLM package, and we identify here the formula, the log scrap regress on total R's, and then this variable D88, 89 plus grant, and then grant 1. Then we identify the data. And what's important is if we're using PLM, we have to identify the index. The index is first is the individual, which is F code, and then the time index. So this is the cross-sectional index, then this is the time index. And then we identify, since it's pooling, we identify the model, and the model is pooling. Okay, and we mentioned before that this is equivalent to an ordinary least squares model. And then we summarize this. Let's see the results. So we have here the pooling model. This is our formula. We're regressing log scrap on these variables. The data is JTrain. We identify the index. The cross-sectional index is F code. And then the time index is here. Okay, it's an unbalanced panel data. And then there are 146 observations. So we have here the coefficients, total R's, D88, D89, okay? And none of them is significant. So if this was significant, it would mean that for every 1 R increase, okay, in training, there will be a 0.46 reduction in the scrap rate. Okay, if this was significant. However, this is not significant. So that's the result of your pooled OLS or your ordinary least squares. If you recall, ordinary least squares, as far as panel data is concerned, ignores the cross-sectional component and the time series component. We can also have other types of regression. Here you have the between estimator. Okay, so in this method, between estimator, the variables are replaced with their means, such that L scrap is the mean for each firm, and so with the others. Okay, so what we can do with this one is model between. We will just make use of this model OLS, which was the previous model, and just change, instead of model is equal to pooling, we change it into model is equal to between. Okay, and then we just use the update function. So which means that it will take on this one, okay, exactly this one, model OLS, but just change the pooling into between. Okay, so we have this, and then let's summarize this. So we can see that the result of this model, okay, it's a one-way individual effect between the model. And we can see here that using the between, using the mean, using the values where the not the mean, I'm sorry, the variables are represented by the means, the averages. And you can see here that, okay, you can see here that the result, the regression output for between is that it's all are insignificant. And you can see here that you have 4 parameters, okay, and you have, this is your n minus k minus 1, which means that there are 49 observations, because you have you got the average only of the each of the variables. Okay, then aside from the between estimators, you can have the first difference. So for the first difference, you just get the log. You just get the difference between the current value and the previous value. So we can do this. We can create this function. Difference is function of x, where x is x minus the log of x. So you just get the value at time t, and then subtract the value at time t minus 1. So you have this, the same object J train, and then we group it by the firm. And then let's create this object mutate. We'll create a variable called dl scrap. So this is the difference of log scrap. Okay, and the difference is defined by this function. So it's difference of log scrap, difference of total R's. Okay, all right. But actually, the difference function can also uses the same formula, where you get the value at time t minus the value of time t minus 1. And then we ungroup them, okay? And then we create our model FD, okay, where we regress the difference values. L scrap, difference total R's, difference of, we just use the grant and not grant underscore 1. Okay, so let's run this and see what the first difference model will give us. Okay, so also the difference total R's and the difference grant, they're not significant. But if they were significant, again, we would say that a 1 unit increase in the difference total R's will lead to a 0.33% improvement in the difference log scrap. So nothing much from the pooled OLS. All right, so we go now to the fixed effect estimator. Okay. For the fixed effect estimator, we're going to take a look at the individual effects of the different firms. So we can use this code model FE. We just update the model OLS, and then we identify the model is within, and then the effect is individual. So we can also run this. It will give us the same answer. Just use the update. But let me just use the complete one here for us to see it. So we're creating this model fixed effect. We're using the PLM function. Same thing. The formula is L scrap regress on our 1, 2, 3, 4, 5 variables using the data. And then same index is F code and year. And then model is within. So this is the difference between the pooling or even the between. We're using here the within, and then we have to include here effect is equal to individual. So let's run this. Okay, and then we can see here now that, so this is the formula, and this is our the result Okay, so you can see here that again the variables are not significant, but if this was significant, it would tell us that a 1 hour increase in training will result into a 0.47% improvement in scrap rate. It's an improvement because the scrap rate is uh, the scrap rate is our dependent variable, and a reduction in the scrap rate means a reduction in scraps. Okay. All right. So I just place here a note here. For every 1 hour increase in training hour for each firm over its mean, there is a corresponding, in our case, B1 is this one, 0.0047 or 0.47%. That's a decrease, which means it's an improvement in the scrap rate, although it's not significant. Now we can indicate what's the individual specific effects. This does not tell us what are the individual specific effects. However, we can do this. Okay, so let's summarize the specific effects. I'm creating this object, individual effects. Okay, it gives us the fixed effects per firm. This fixed effects does not vary over time. That's why it's called fixed. Okay, so let's create this object IF, which is, I'm using this function fix F, and then the model is FE, the type is the mean. Okay, and then we get the head. Okay, so let's run this first. Okay, so you can see here the first 10 values. Okay, so this is the value this is the individual specific effect for fixed effect for firm 1, for firm 2, for firm 3. So what's the meaning of this? Okay, so on the average, firm 1 has a reduction, negative 3.27, means that it has a reduction or an improvement in its log scrap. For 4110, it's positive, which means the scrap rate is increasing. This is the average increase in scrap rate. Same thing for 563, okay, ending in 63, it's 1.29, okay, etc. So these are the specific individual effects. Okay, so we can summarize this and make it into a table. So we have here the firm, the estimate, the standard error, and we can see that it's significant. Okay. Okay, we can see here the all things being equal, and on the average, firm 23 has a log scrap value of 3.27, okay, 3.28 approximately, which means the average is a reduction or an improvement in the scrap rate. So you can find here all the companies, all the firms, some of the values are significant, but some are not, which means that their values not different from zero. And you can see here the average of the individual effects is practically zero, which is expected. It's supposed to be zero. So for the 49 firms, okay, you have here the average is zero. The minimum is negative 3.523, and the maximum is 2.722. So what's the meaning of this? What's the meaning of this? So firm 1 has a lower scrap rate compared to the average firm, okay, lower by 3.27, okay, which means that uh, there's a reason why these firms have this average scrap rate, okay? We may not know what in the firms make them have higher or lower scrap rate, but there's something about them that make it such, and we'll be able to quantify it. This one, okay? So, uh, of course, what can be done is to examine more in greater detail other factors that make the firm, for example, 523. Why does it have a uh, a lower scrap rate as compared to the other firms? And I think the highest is 3.5. Okay, this one. I'm sorry. Okay, I can't see it from this list. Anyway, all right. So that's the fixed effect model. You can also use the fixed effect model. Okay, you can perform this, but using another way, which is what we call the dummy variable regression. Okay, so how do we do that? So this will give the same result as fixed effect. Okay, so the model that we're going to do is model dummy variable. Okay, we're going to create a dummy variable for the firm F code. So we're using PLM and then same formula. Okay, however, this time we're going to include as part of the regressor F code, which is the firm. And we're going to make sure that it is a factor. Same everything, okay? But notice here for dummy variable, we're using pooling, okay? This is okay because we added F code or the firm as a predictor. So if you recall, in multiple linear regression, if we add a factor, what will happen is one level will be used as a benchmark. So in this case, what first appears alphabetically, that's the first firm, which is 523 here, 523. So this will be used as a benchmark, so it will not appear in the output, okay? And all the others will be interpreted in relation to that, to the benchmark. So let's run this, and you can see the first firm, 523, is not here, okay? It has been normalized. It was given a value of 0. And if you notice, for 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 538, the value is 3.7317, right? However, in the fixed effects here, 38 has 0.45. Okay, so why are they different? So let me just use this, or just below. Why are they different? Are they really different? So the value in the fixed effect for company, that company 538 is that amount, but here it's 3.73. Okay, so let's just validate this. So this one is in the fixed effect model. This one is in the dummy variable. Okay, but remember, class, that for the dummy variable, this is in reference to this is in reference to this is in reference to the benchmark, which is 532, and the value of 532 is this one. All right. Okay, so what made this difference? Okay, so this is the value of 3.2. This is the value of 3.8. So if you get the difference, so this is 3.2 minus the value of 3.8, Control C. This one, this one. So that's 3, negative 3.73. So what does that mean? Which is this one. Okay, so it means that, remember how do you interpret 3.73? Okay, positive, which means it's a, since the log scrap is negative in connotation, it means that the scrap of firm 538 is greater than 3 than 3532 by 3.73. Okay, so that makes sense. This is the average scrap rate of 3.2. This is the average scrap rate of 3.8. If you get the difference of that, it's 3.73. Okay, so again, so how do we interpret this? 538 has 3.73 scrap rate more than 3.2. Okay, but since we're measuring the scrap, then that means that then 538 produces more scrap than 3.2. Okay, and the others are the same. If you take a look at the other parameters, total Rs is 0.0047 and it's not significant. It's the same here for our fixed effect here, 0.0047, and it's not significant. So all things are the same, only that for the for the uh, for the fixed effect, okay, it does not give us the you can, of course, you can, from the fixed effect, you can, okay, generate this to determine the average log scrap, the scrap rate for each of the company. Okay, but in the dummy variable regression, okay, you can generate the same. However, it is benchmarked against your reference variable, which is the first, which is 532. Okay, so that's your your fixed effect. So for the fixed effect, we would want to see the individual effects of the of the uh, units. Okay, so where are we? Just okay. Now you notice that, sorry, there's a difference between the, let's go here. Let me just close this. All right, so let me just run this again, this fixed effect. And you can see that the R squared is around 0.22. Okay, R squared is 0.22 or 23%. However, with the dummy variable, the R squared is around 0.92. Okay, so there's a difference between the R squared of the fixed effect and the R squared of the dummy variable. The difference lies in how uh, the computation is done. Okay, let me go back here. Okay, for the fixed effect, what's done is that the uh, the y is actually your demeaned y. Okay, which means that for the log scrap, the dependent variable is your log scrap less your mean of your log scrap. So because of this, because we're demeaning it, we're removing the mean from the dependent variable log scrap, then the variation tends to be uh, to be decreased. So let's take a look at this. So the predicted value is the fitted value of model FE. Now Ry, we're using this P model that responds. So this is your demeaned y, and we can compute here the total sum of the squares. It's just the predicted value minus the average of y. So this is the model sum of the squares. And then we also have the error sum of the squares, which is just the residual of our model f e squared. And then we can now get the r squared, which is just the total sum of the squares. Sorry, the model sum of the squares divided by the model sum of the squares plus the error sum of the squares. So if you run this, you'll notice that you get here the okay. So this is your the model sum of the squares. This is your error sum of the squares, and this is your r squared. Okay. So if we do that for the dummy variable, okay. So the y here, the y here is not the demeaned y. Okay. So for the model, for the dummy variable, we're just using the log scrap itself and not the demeaned y. Okay, so if you look at this computation, same thing, only that here, okay, our y is the y for the model, the dummy variable model is exactly the log scrap, while the y for the fixed effect model is the demeaned log scrap. Okay, so if we run this, you can see now that okay, the error sum of the squared, residual sum of the squared is the same, 24.3109. It's the same as the one above here, exactly the same. However, the difference is in the model sum of the squares. This is 7.2, while for our dummy variable, it's 286.65. So, which means that in the fixed effect model, since we're using for the dependent variable, we're not using the log scrap, but rather the demeaned log scrap, which means the log scrap minus the mean of the log scrap. That process will remove variation, unlike the dummy variable where we did not use the demeaned log scrap, we just use the actual log scrap. So you have a higher model sum of the squares. Okay, so that's why your adjusted your r squared is higher. So that explains why there's a difference between the R squared for your fixed effect and for your dummy variable model. Okay, but they produce the same result. Okay, same coefficients for your regressors, and same uh, technically the same value for your individual effects, only that it's presented in a different way. So for the fixed effect, you can get the actual average log scrap per firm, while for the dummy variable, you have to benchmark it against the reference variable. Okay, the last one, the last model. So we have pooled, we have fixed effect, we have the random effect, or this is called the random intercept or partial pooling. So same thing, we can also generate the model using an update, and then we just define the model is equal to random, and then the random dot method is equal to Walhas. There are different random methods, but this is one of the more popular ones, the Walhas. Okay, so the long formula, the actual formula is this one. Same thing, same everything. We just change the model to random, and then we identify the method. Okay, so if you run this, okay, you'll notice that there's something different with the random effects model. So this is using the Wallace-Hussein transformation. The transformation is done in order to make your model more efficient. Okay, so let's not go into the nitty-gritty details of that. So there are different transformations, and they all seek to make the model more efficient. So here you have a different uh, uh, output here. You have the idiosyncratic and individual and theta. Okay, so we'll focus on this. We'll see that the idiosyncratic, okay, has a share of 0.118, while the individual has a share of 0.882. So what does that mean? And we also have this theta, yeah, the median at 0.7938. So, all right, so let me first discuss theta. Let me just read through my comments here. Okay, the theta refers to the variance component associated with the random effects. Okay, so we know that the random effects model, it's similar to pooling. It's a type of regression model that accounts for both fixed effects, okay, and random effects. So it takes a look at both. It's a combination of fixed effect and random effects. Okay, so for fixed effect, typically it's a predictors or independent variables, and the random effects, which represent unobserved or latent variables that are assumed to have a random effect on the outcome variable. Okay, so I have here some notes. Okay, so as I mentioned, the variance of the dependent variable have two components. You have the fixed effects and the random effects. So for fixed effect, you're looking at the variation in the dependent variable that is explained by fixed effects. Okay, so the fixed effects, these are predictors that are the predictors included in the model. Okay, so effects of the independent variables. Okay, for the random effects, these are additional variation in the dependent variable that is attributed to random effects. Okay, so I hope this is clear. In random effects model, there are two types of variation attribute that as far as the variance of the dependent variable is concerned. May dalawang components yan. No? First is the fixed effect variance, and then the random effects variance. The fixed effect variance is due to, okay, due to the predictors included in the model. Okay. On the other hand, random effects are those that are not included in the model. These are variation that is attributed not to the independent variable, but rather to random effects. Okay, so theta specifically refers to the parameter that represents the variance of the random effects in the model. Okay, it quantifies the amount of variability. Okay, so if we take a look here, okay, so you have here effects. This is your fixed effects, okay, and this is your random effects, your theta. Okay, so just to explain the idiosyncratic and the individual. So the individual effects refer to the specific effects of each individual entity, as the name suggests, no? Individual entity. On the other hand, the idiosyncratic effects, or this is the error component, no? Also known as individual specific effects or unobserved heterogeneity. It captures the unique characteristics of individual entities that are not accounted for by the observed value variables in the model. Okay, so typically assumed to be uncorrelated with the IVs. All right, so that's a difference between the two. And you have the share, okay? We have the share here, 0.11 and 0.88. So what does that mean? What does the 0.11 and 0.88 mean? Okay, but by the way, in the random effects, the total R's is significant at 10% level of significance. So that's for every 1 R increase in total training R's, you have a 0.47% decrease in the scrap rate. Okay, so let me explain that. What does a 0.11 and 0.88 or 0.89 mean? So 0.11 is for the idiosyncratic, okay, and this represents the variance of the error term in the model. Okay, so we said that idiosyncratic refers to the error, the error, the variance of the error. A value of 0.11 indicates that approximately 11% of the total variation in the dependent variable is due to individual specific random fluctuations that are not explained by the model's predictors. Okay, so 11% cannot be explained, while 89% represents the variance of the individual specific effects in the model. Okay, 89% of the total variation in the dependent variable is due to the differences between individuals that are constant over time. Okay, so overall, this suggests that a substantial portion of the variability in the dependent variable is explained by individual specific characteristics. Okay. All right. So we can of course show the computation for the theta, but I'll just this code is provided for you, or okay, anyway, it's very easy to copy that. So we will now go to the comparison of the model. So you have pooling, you have fixed effect, and you have random effects. So the question is, which of the three models should we use? So uh, we can use the statistical test to determine what's the if there's okay if pooled OLS is better than fixed effect. First, let's compare pooled and fixed effect. And we can use the F test. Okay. So in the F test, the null hypothesis is that there are no fixed effects, which means that OLS is better. So this is the code PF test, model FE, and model OLS. If we run this, so here you have the alternative hypothesis that there are fixed effects, there are significant effects, and the p-value is very much less than 0.05. So this is indicating that this suggests that we reject the null hypothesis that there are no fixed effects. There are fixed effects which have to be accounted for. So this tells us that the fixed effects model is preferred to the uh, pooled OLS method. Okay, so let's now go to, so this is the F test, okay? Okay, sorry, this should be here. Sorry, this got doubled. Okay, so we have done that, and we have shown that there are indeed uh, fixed effects. We can also use the Hausman test. Okay, so for the Hausman test, the null hypothesis is fixed effect model is consistent and efficient, just like the F test. If we run this, you're using the Hausman test, pH test, and the null hypothesis here is different. For the F test, the null hypothesis is that there are no fixed effects. So we reject that, okay, because the p-value is less than 0.05. However, for the Hausman test, the null hypothesis is that the fixed effect is consistent and efficient. And the p-value is way above 0.05. Therefore, we fail to reject this. So therefore, indeed, based on these two tests, the fixed effect is better compared to pooled. Now let's compare the pooled and random effects. We use again the pH test, the Hausman test. Same thing. The null hypothesis is that the random effects model is consistent and efficient. If I run this and we get a p-value of 0.7052, which leads into a failure to reject the null hypothesis. Therefore, the random effects is better. It's consistent and efficient. And finally, we have a comparison between the fixed effect and the random effects. Okay, we're also going to use the Hausman test for this. Okay, let's just compare this. So take note that for the fixed effect, these were our parameters. So maybe I'll just copy this. So we're trying to compare if there's a difference between the parameters, the estimates. You have 0.004, 0.07, and for the random effects, 0.004, 0.07. Okay, there seems to be a difference between the two. So we're going to test whether really the fixed effect and the random effects are practically the same. Okay. So what we're going to do here is we're going to use the Hausman test. Okay, the null hypothesis here is that there's no difference between I didn't write here, the null actually it's the no difference which means if there's no difference between RE and FE, then which means RE is better because it is efficient. Okay. The null hypothesis is that there's not much difference no statistical difference between your RE and FE. So if there's no difference between them, then the random effect is better. Okay. So if the Hausman test statistic is insignificant, which means we cannot reject this. Then the RE is better. If it is significant, then which means there's no difference. Uh, if it is significant, then I'm sorry, no difference between. This should be the alternative. There is a difference. Okay. So if the null hypothesis is that there is a difference between RE and FE, which means if there's a difference between them, then we go for RE, because RE is more efficient. However, if there's no difference between them, which means we're rejecting this, then we use the FE estimator because it is consistent. All right, so let's run this. And we find that the p-value is 0.9425, okay, which means that 0.9425, we fail to reject the null hypothesis, which means that there's a difference between RE and FE. Therefore, since RE is more efficient, then we choose RE, random effects. So for this data, the random effects model is the preferred model. Okay, so we were able to determine that in this case, in this data, the random effects model is better. So we can identify our model to be the summary. So this will be our model itself. Okay, although total R's is just significant at 10%. Now, of course, we're getting these results because most probably because we did not include other variables. It was just meant to for us to have a working knowledge of how it is to do pooled OLS, fixed effect, and random effects. Okay, and we were able to discuss what's the meaning of the effects and the theta here. Okay, so lastly, we go to diagnostics. Let's first take a look at if there's multicollinearity among the variables. So let's rename our model RE to be the best model. Okay, and then we can use the VIF, the variance inflation factor of the best model. Let's give it a name, VIF values, and let's print it. So we can find here that the VIF is less than 5, so which means that there is no multicollinearity between our variables, so that's okay. And then here, for the heteroscedasticity, okay, we can use the Bruce-Pagan test. Okay, so this is from the LM test package. And let's create an object, BP result. And if the residuals of the best model are heteroscedastic, then the null hypothesis is that the residuals are homoscedastic. Then the p-value is 0.6758, which means we fail to reject the null hypothesis. So the residuals are homoscedastic. In the event that we have a p-value that's less than 0.05, then we can modify our model, okay, by using the LM test. We do this COEF test, coefficient test, and then we are going to introduce robust standard errors, okay, from the sandwich package. We have variance, covariance, heteroscedasticity consistent, then type is equal to HC1. So it would be, this is, we have discussed this, the robust standard errors. This will change our standard errors into robust standard errors. So if we run this, okay, and this will now be our new standard errors, okay, and that addresses now our are heteroscedasticity. Now notice that this is not a problem in this case. I just I just illustrated this for you to be guided in case that there's heteroscedasticity. And then we have serial correlation. Okay, let's see if there's serial correlation in the residuals. And we're going to use this uh, Bruce uh, Bruce Godfrey Wooldridge test. And the null hypothesis is that there's no serial correlation in the residuals. Sorry. And the p-value is greater than 0.05, then there's no serial correlation. And so that's okay. And then finally, you have the normal distribution. Okay. And the null hypothesis is that the residuals are normally distributed. And we find here that the residuals are not normally distributed. Okay. So that ends my very brief discussion of the methodology behind panel data regression. Okay, thank you so much.